Welcome back. Today we're going to begin Unit 5 on exponential and logarithmic functions. First, we're going to look at just introducing exponential and logarithmic functions, and then we'll start solving some equations and look at some applications of them. To start, let's look at exponential equations, and I'm going to actually add that these are functions. I'm not sure why I changed that, but that's okay. And here we have the models of an exponential function. F of x equals b to the x, or as an equation, y equals b to the x. Now for these exponential functions, b is greater than 0, and b does not equal 1. We call b the base of your exponential function. So here I've got some examples of exponential functions. Y equals 2 to the x, g of x equals 10 to the x, h of x equals 3 to the x plus 1. What makes these functions here different than anything we've seen previously? We've seen exponents before. The difference in these examples are that the exponent is a variable. When we were looking at polynomials like x squared or x cubed, our variable was actually the base and our exponent was a constant. So that's the difference between our exponential functions and our polynomial or our power functions. Evaluate an exponential function. F of x equals 5 to the x. We want you to find f of 4. So that tells me that we want to plug in 4 for x. So f of 4 is 5 to the 4th power. Now you guys can use your calculator to do this. If you don't know the buttons that you're going to use, bring it to class and we'll look at your calculator individually. But 5 to the 4th is 625. Now if you didn't have a calculator or you're not sure, you can still do this by hand. 5 to the 4th is 5 times 5 times 5 times 5. So 4 5s being multiplied. G of x equals 4.3 times 1.4 to the x. Find g of 3. Again, we're just substituting in 3 for x. So we have 4.3 times 1.4 cubed. Now when we're evaluating this, if we want to take it step by step, remember that you have to do 1.4 cubed first. Our order of operations, exponents come before multiplication. But when we evaluate this, we get 11.7992. Again, if you're having trouble evaluating this on your calculator at home, bring it into class and I can show you how to type it in based on your individual calculator. So we can graph exponential functions by making a table of values. We're going to graph f of x equals 2 to the x. Now, for an exponential function, we don't actually have any domain restrictions. So we're going to plug in -3, -2, -1, 0, 1, 2, and 3, just so that we can see the relationship of the points and actually get a really good picture for this. When we plug in x equals -3, we have 2 to the -3rd power. Well, when we think about negative exponents, how do we make them positive? I want an exact value here. I don't want a decimal approximation. Even though we'll use it to graph that point, we still want to know how to simplify this expression. So I'm going to come down here just to show you guys 2 to the -3rd, we can make it a fraction by putting it over 1. And if you have a term with a negative exponent, to make that exponent positive, you just move that to the other side of the fraction. So this is actually equal to 1 over 2 cubed, which is 1 over 8. If I take 2 and raise it to the -2 power, that's going to be 1 over 2 squared, or 1 over 4. 2 to the -1 is 1/2. What is anything raised to a power of 0? Anything raised to a power of 0 is 1. 2 to the 1st power is 2. 2 squared is 4. and 2 cubed is 8. So we're going to plot these points, starting with the easy points first. We have 0, 1, 1, 2, 2, 4, 3, 8. And then -1, we're at 1/2. That one's right there. -2, we're at 1/4, so a little bit closer. -3, we're at 1/8, which is even closer to the x-axis, isn't it? But not on the x-axis, so I'm going to try to approximate it, getting closer. But what's going to happen as I plug in more negative values? As my denominator gets larger, which is what's happening, look at my x values are getting more negative, the denominators are getting larger. I've got 1 divided by a very large number. Well, although it is a very, very small decimal, it's still never going to equal 0. We actually have a horizontal asymptote on our x-axis. We're never going to hit that x-axis there. So my graph is this nice, pretty curve going up. What's the domain of this function? Looking at the graph, we can see that the domain is -infinity to +infinity. And what about the range? The range, we see a restriction, don't we? Our range starts at 0, starts here at our x-axis, and then goes all the way up to +infinity. Do we include our value y equals 0? And the answer is no, because like we were talking about before, 1 divided by 1,000,000 is still not 0. It's really small, but not 0. So we approach the x-axis, but we don't ever actually touch it. Okay, let's try another one with a different base. F of x equals 1/2 to the x. So we're going to plug in the same 6 or 7 values, -3, -2, -1, 0, 1, 2, and 3. Now when we're evaluating this, let's start with the easy ones. 1/2 to a power of 0 is still 1. 1/2 to the first power is 1/2. 1/2 squared is actually 1/4. Remember, you have to square the numerator and the denominator of that. 1/2 cubed is going to be 1/8. Now let's look at 1/2 to the -1. I'm going to go down here to show this. 1/2 to the power of -1. That exponent we can actually distribute to the top and to the bottom. So this is 1 to the -1 divided by 2 to the -1. Looking at my numerator, 1 raised to any power is always just going to be 1. So we have 1/2 to the -1. And to get rid of that negative exponent, we move it to the other side of the fraction. So this ends up becoming 2 to the power of 1. So then 1/2 to the -2 is going to be 4. And 1/2 to a power of -3 is going to be 8. Now when we look at these y values, hopefully they seem pretty familiar, maybe from our previous example. Okay, let's go ahead and plot these. Again, start with your easy points. We've got 0, 1, -1, 2, -2, 4, -3, 8. 1, 1/2 is pretty easy. 2, 1/4, 3, 1/8. Again, we see that same shape where we're approaching that x-axis, but now we're going down, aren't we? The domain of this graph, same as we had before, -infinity to +infinity. And we see that the range is the same as well, 0 to +infinity. The only difference is that the previous example was increasing, where this one is decreasing. So when you're graphing a exponential function, just set up a table of values. That'll work just fine. Some characteristics of our exponential function, f of x equals b to the x. Now we're going to call this our parent function. Even though there's infinitely many parent functions because we can change the value of b, we'll talk about that in these two bullets here. But otherwise, all of these functions are going to have these same characteristics. Now again, this does not account for any type of transformations, no vertical shifts, no vertical horizontal shifts, no reflections, things like that. So the domain for all of our exponential functions, these parent functions, is going to be the same, negative infinity to positive infinity. We saw that in the last two graphs, didn't we? The range is going to be 0 to positive infinity. Now, what's going to modify the range? The range was that what we were looking at on the y-axis. The only things that will modify the range are going to be vertical shifts, so taking that graph and moving it up or down, and also possibly a vertical reflection, so a reflection about the x-axis would affect the range. If you look back at your last two graphs, what point did both of those graphs go through? They both went through the point 0, 1. Now, if the base of your exponential is greater than 1, then the graph is monotone increasing. Which is just a fancy way of saying that the graph is always increasing. And we saw that with our first function, 2 to the x. We had a picture that looked like this. So as long as the base is greater than 1, it's going to be increasing like this one. Now, if your base is between 0 and 1, remember that your base can't be negative. It's got to be greater than 0. Then it's monotone decreasing. And that's just like the last graph that we did, 1/2 to the x. So we'll see that graph with a decreasing shape. Our parent function f of x equals b to the x is 1 to 1. What does that mean? Do you guys remember this was from a couple units ago? 1 to 1 indicates that it passes the horizontal line test, right? It's a function that also passes the horizontal line test, so it passes the vertical and the horizontal. And that tells us that the inverse of this function is a function. So inverses are coming back in this unit. We're going to talk more about what we are doing in Unit 2 with finding inverse functions, the relationship between domain and range of inverse functions in this unit. Also, f of x equals b to the x, that parent function never touches or crosses the x-axis. We have that horizontal asymptote at y equals 0. So again, these are the characteristics of just the parent function. We're not including any shifts or reflections. Let's graph f of x equals 2 to the x plus 1 using those transformations. If I look at this, my parent function is y equals 2 to the x. Now I chose this because we've already graphed y equals 2 to the x, so we know the original points. And this plus 1 is our transformation. That's affecting our input, so it's a horizontal shift. And remember that the horizontal shift, the rules are a little backwards, so we're actually going to shift this to the left 1. So if I think about using transformation, and I'm going to use the points that I graphed before for my parent function. In white, I'm going to graph y equals 2 to the x. So we had 0, 1, 1, 2, 2, 4, negative 1, 1/2, negative 2, 1/4. These are the points that we have on our first example that we were graphing. Again, those are the points from our parent function, y equals 2 to the x. Now in red, I'm going to take all of these and apply my transformation. I'm going to shift them to the left one, not right one. So the graph in red represents f of x. Now, if you don't want to use transformations, you can always make a table of values, pick a couple x values, plug them in. Again, when we're using a table of values, just make sure that you understand what the graph is supposed to look like. That way you can double check to make sure that your points fall where they need to. F of x equals negative 2 to the x plus 1. Again, using that parent function of y equals 2 to the x, what are my transformations? Well, I have a transformation of this negative since it's affecting the output. Exponents 2 to the x comes before multiplying by that negative 1. So it's going to be a vertical reflection, which reflects over the x-axis. And this plus 1 is going to shift it up 1. So again, I'm going to use those points that we used in that first example. We had 0, 1, 1, 2, 2, 4, negative 1, 1/2, negative 2, 1/4. These are the points for my parent function. And if you guys recall, when we're graphing a sequence of transformations, we need to go in a particular order. Specifically, this vertical shift has to always occur last. So we're going to take all of our points and first reflect them and then shift them up 1. So I'm going to show first a graph in, well, let's use blue. The graph in blue is going to be our reflection about the x-axis. So all I'm doing is taking those original points and flipping them about the x-axis, and these are the points that we have in blue here. And now I'm going to take all of those points and shift them up 1. So when I shift them up 1, what ends up changing in this graph? Well, certainly the range is changing, isn't it? And we can also see, because the range changed, that our horizontal asymptote also changed. It was originally on the x-axis. When we shift it up 1, that vertical shift is also going to push that horizontal asymptote up as well. So the domain for this new function is actually, or our domain is still negative infinity to infinity. Our range is what changed. Our range, if we're looking at the graph in red, is from 0 to positive 1. I'm sorry, negative infinity, not 0. Negative infinity to positive 1. Always you have the option. I didn't utilize the table of values here, but you can always make a table of values as well. Identifying the vertical shift and where your horizontal asymptote will help you make sure that your graph looks nice. In your homework on the test, you do have to graph your horizontal asymptote. If it's not there, you're not going to have a complete graph. So make sure you start with that if you need to, especially when we're using a table of values. The natural number is e, which is actually approximately 2.71828. It's an irrational number. Think of it similar to pi. The natural number is called the natural number because it's a very common function, a common base for exponential functions that represent relationships in nature. So using this, let's look at an application. Oops, there you go. We're given a function, f of x equals 1066 e to the 0.042x, and this models the gray wolf population of the Western Great Lakes X years after 1978. We want to use this to estimate the population in the year 2017. So if I want to find the population in the year 2017, and X represents the years after 1978, X is equal to 2017 minus 1978, which is 39. And now we're just going to substitute this into our function. F of 39 equals 1066 e to the 0.042 times 39 power. Now, if you're looking for e on your calculator, you want to look for a button that says ln. So look for a button that says that, and it's usually going to be a second function to that. So you're going to have to press second ln to get your e to an exponent to come up. Again, if you're having trouble finding that, bring it into class and we can look at it on your calculator. But when we evaluate this, we get 5,484.43, which when we're talking about wolves, we can't have a fraction of a wolf. As long as we've got part of one, we're going to round up to 5,485 wolves. Okay, so just to recap, our exponential functions are characterized by having an exponent as a variable, or a variable as an exponent, excuse me. We looked at evaluating an exponential function. We're using the power key on our calculator, and we also graphed exponential functions. We can always just make a table of values to graph, but we can still use the concepts of transformations if we recognize a parent function in our given function. And last, we talked about our natural number e, which we're going to see a little bit more when we talk about logarithms as well. And we saw an excellent example of an application where we'll be using exponential functions. And we'll look more at those types of examples at the very end of this unit. So we'll see you guys next time for logarithmic functions.